There is a moment at night when silence becomes strange, not the silence of tiredness, not the kind that settles in when the noise outside slowly fades and the city finally gives up. This is a different kind of silence, denser, older, harder to name. It is the silence you feel when you lift your eyes toward the sky and truly realize, not just intellectually but somewhere deeper, that what you're looking at no longer exists. The stars you see tonight are not there. Some died millions of years ago, some died billions of years ago. What reaches your eyes is only light, old light, surviving light. Light that has been travelling through the void for so long that the stars which produced it have already collapsed, exploded, or quietly faded into darkness. The image you see is a ghost, a beautiful ancient ghost that crossed an unimaginable distance just to reach the back of your eye on this night. Wherever you are, stop for a second on that. Every time you look at the sky, you're looking backward in time. The moon you see is the moon as it was, 1¼ seconds ago. The sun is 8 minutes in the past. Proxima Centauri, the nearest star beyond our solar system, is 4 years behind, and the faint smudge of the Andromeda galaxy, just barely visible to the naked eye on a clear night, is the universe as it looked 2.5 million years ago, before our species existed, before the first humans stood upright and looked up at the same sky with completely different eyes. The further you look, the further back you go. Where are you right now as you listen to this? In bed, lights off, phone resting on the pillow beside you? On the couch, wrapped in something soft, the room almost dark? Maybe you have headphones on and the world outside has stopped existing. Maybe you're somewhere between sleep and wakefulness, in that gentle border zone where thoughts slow down and the mind starts to drift. Wherever you are, it is exactly the right place for this. What we are about to explore is one of those stories that changes something in you, not violently, not in a way that frightens or overwhelms, in a quiet way, the way a good question changes you. It opens something, it shifts the angle just slightly. And suddenly, things that seem settled do not feel quite so settled anymore. When it ends, it leaves you with a strange sensation, somewhere in your chest, the feeling of having touched something enormous and not yet having the words to describe what it was. The story begins with a telescope, not just any telescope, the most powerful instrument ever built by human hands. 18 hexagonal golden mirrors, each coated in a layer of gold just a few atoms thick, arranged into a surface as wide as a tennis court. A machine that took 30 years to design, over $10 billion to build, and a single rocket launch on Christmas morning 2021 to send into the void. It travelled for a month through deep space before reaching its destination, a gravitational sweet spot called the second Lagrange point, 1.5 million kilometres from Earth. There, in permanent shadow, shielded from the sun, cooled to temperatures colder than anything that occurs naturally in our solar system, the James Webb Space Telescope opened its golden eye, and it began to look. Since its first images in the summer of 2022, Webb has not stopped astonishing us. Galaxies being born, atmospheres of distant planets, star nurseries hidden behind clouds of dust that no instrument had ever pierced before. But beneath the wonder, something else has been growing. A tension, a quiet but persistent unease spreading through the scientific community. Because the more Webb looks, the more it finds things that do not fit, things that should not be there, things that our best theories built and refined over nearly a century, simply cannot explain. Scientists around the world are looking at the data and saying the same thing, some cautiously, some openly. Something does not add up. And that phrase, something does not add up, is perhaps the most exciting sentence that science can ever produce. To understand why what James Webb is finding is so deeply unsettling, you first need to understand what we thought we knew, the story we told ourselves about the universe, where it came from, how it grew, and how it became the vast, dark, star-filled place it is today. That story begins not with a telescope, but with a shift in light. It was 1929. An American astronomer named Edwin Hubble was working at the Mount Wilson Observatory in California, studying the faint smudges of light that appeared in his photographs of the night sky. At the time, there was still genuine scientific debate about what these smudges were. Some believed they were clouds of gas and dust within our own Milky Way. Others suspected they might be entire separate galaxies, island universes, lying far beyond the boundaries of our own. Hubble had already helped settle that debate. He had measured the distance to several of these objects and confirmed they were indeed separate galaxies, enormously far away. But now he was looking at something else, at the light itself, and more specifically at where that light fell along the spectrum. He noticed something that would change science forever. The light from these galaxies was shifted toward the red end of the spectrum. In physics, this is called redshift. It occurs because of the Doppler effect, the same principle that causes the pitch of a passing ambulance siren to drop as it moves away from you. When a source of light moves away from an observer, the waves of light get stretched out. They become longer, and longer wavelengths correspond to the red end of the visible spectrum. The faster the source moves away, the more pronounced the shift. Hubble measured this shift in galaxy after galaxy, and he found something extraordinary. Not only were almost all of them redshifted, meaning almost all of them were moving away from us, but there was a clear pattern. The farther a galaxy was, the faster it was receding. Distance and velocity were linked. The universe was not static. It was not sitting still, eternal and unchanging, the way most scientists had assumed. It was expanding. The implications took time to sink in, even for Hubble himself. If the universe is expanding now, then in the past it must have been smaller. Wind the clock back far enough, and all of that expanding space converges, tightens, compresses into something inconceivably dense and hot. A state so extreme that our normal understanding of physics begins to break down at its edges. We call what came from that moment the Big Bang. Not an explosion in space, as it is often imagined, but an explosion of space itself, the very fabric of reality stretching outward from an unimaginably compressed beginning, carrying matter and energy along with it. For decades, scientists built on this foundation. They calculated the age of the universe from the rate of expansion, arriving at approximately 13.8 billion years. They detected the cosmic microwave background radiation, the faint thermal echo of that original fireball still washing over us from every direction of the sky. They worked out a detailed timeline of how the universe evolved, how the first hydrogen and helium atoms formed in the minutes after the Big Bang, how gravity slowly pulled matter together over hundreds of millions of years, how the first stars eventually ignited in the darkness and began the long chain of events that would lead to planets, oceans, life, and a species curious enough to build telescopes and ask where it all came from. It was a story with extraordinary explanatory power, supported by multiple independent lines of evidence, refined by generations of brilliant minds until it fit together with remarkable precision. By any measure, one of the greatest intellectual achievements in human history. And then Webb pointed its golden mirrors at the early universe, and the story started quietly but unmistakably to crack. The crack didn't announce itself dramatically. There was no single moment where an alarm went off, no press conference where a scientist stood up and said that everything we knew was wrong. It happened the way most revolutions in science happen, slowly, through accumulating data, through numbers that didn't quite line up, through results that were checked and rechecked and checked again and still refused to behave the way they were supposed to. It started with galaxies. When the James Webb Space Telescope was being designed and built, one of its primary scientific goals was to observe the very first galaxies, the ones that formed in the earliest epochs of the universe, just a few 100 million years after the Big Bang. This was genuinely uncharted territory. Previous telescopes, including Hubble, had managed to peer back to about 400 to 500 million years after the beginning. Webb, with its vastly superior infrared sensitivity, was designed to push that boundary, to see further back into the deeper darkness and catch a glimpse of the universe in its true infancy. Scientists knew what they expected to find there. In the earlier stages of the universe, according to our standard models, galaxies should still be forming, small, irregular, chaotic, clumps of gas and young stars just beginning to coalesce under the pull of gravity. The universe at that age was like a city in its first days of construction. Scattered materials, rough outlines, nothing yet finished or settled. You wouldn't expect to find skyscrapers in a place where the concrete was barely dry. Webb looked, and it found skyscrapers, not metaphorical ones. Actual massive, fully formed, structurally complex galaxies existing at a time when, according to everything we understood, they had no business being there. Galaxies with billions of stars already in place. Galaxies with organized structures. Galaxies that looked, in some cases, remarkably similar to the large mature galaxies we see in the universe today. Except they were observed at a point in cosmic history when the universe was less than 700 million years old. To put that in perspective, the universe is approximately 13.8 billion years old. These galaxies were observed when the universe was barely 5% of its current age, and yet they were already enormous, already complex, already ancient-looking in a universe that had barely begun. The astronomers who first saw these results did what scientists always do when they get an unexpected result. They assumed they had made a mistake. They checked the data. They recalibrated the instruments. They looked for contamination in the signal, for errors in the redshift measurements, for any possible alternative explanation that might make the problem go away. They ran the numbers through different models, applied different corrections, consulted with colleagues at other institutions who had no stake in the outcome. The galaxies didn't go away. In fact, the more carefully scientists looked, the more of them they found. Not just a handful of anomalous cases that might be explained away as statistical flukes. Dozens of them, observed across multiple independent studies, confirmed by different research teams working with different methodologies. A paper published in 2023 described a sample of galaxies so massive, observed so early in cosmic history, that the authors themselves wrote that the findings were, in their words, difficult to reconcile with our current understanding of galaxy formation. One researcher, Ivo Labbé from Swinburne University, described the situation with a phrase that has since been quoted widely. He said that some of these galaxies were so unexpectedly large that if confirmed, it would require the universe to have converted nearly all of its available matter into stars with extraordinary efficiency, far beyond anything our models predict as possible. Think about what that means. Our models of galaxy formation are not simple guesses. They are built on decades of observation, refined through supercomputer simulations that model the behavior of dark matter, gas, gravity, and radiation across billions of years. They're among the most sophisticated predictive tools in all of science, and yet Webb is finding objects that those models say should not exist, or at least should not exist yet. Something formed these galaxies faster than anything we thought possible. Something drove star formation at rates that our current physics struggles to account for, and the universe apparently didn't get the memo that it was supposed to take its time. But the massive early galaxies were only the beginning. As Webb continued its observations and the data kept flowing back to Earth, another problem began to surface, one that cut even deeper into the foundations of cosmology. This one didn't just challenge our understanding of how galaxies form, it challenged our understanding of how fast the universe itself is expanding. That is a much more fundamental problem. It has a name. Scientists call it the Hubble tension. To understand what the Hubble tension is, you need to go back to Edwin Hubble's original discovery. The observation that the universe is expanding. The rate of that expansion is described by a number called the Hubble constant, written as h0. It tells you how fast a galaxy is moving away from us for every megaparsec of distance, a megaparsec being roughly 3.26 million light-years. The higher the Hubble constant, the faster the universe is expanding. For decades, measuring this number precisely was one of the central challenges of cosmology. Early estimates varied wildly, but over time, as instruments improved, two main methods emerged. Both were considered highly reliable. The first method works by studying the cosmic microwave background, that faint thermal afterglow of the Big Bang that fills the entire sky. By analysing the tiny fluctuations in temperature across this background, scientists can model the early universe with extraordinary precision and calculate what the Hubble constant should be. This method, most famously used by the Planck satellite, gives a value of approximately 67 kilometers per second per megaparsec. The second method works by building what astronomers call the cosmic distance ladder. You start with nearby objects whose distances you can measure directly, stars called Cepheid variables, which pulse at rates directly related to their true brightness, allowing you to calculate exactly how far away they are. You use those to calibrate the distances to slightly farther objects. Then you use those to reach even farther, until you get to objects so distant that their redshift directly tells you the expansion rate. This method consistently gives a value of approximately 73 kilometers per second per megaparsec, 67 versus 73. On the surface, that might not sound like a dramatic difference. But in cosmology, where measurements are made with extraordinary precision and error bars are carefully calculated, this discrepancy is enormous, statistically significant at a level that scientists take extremely seriously. The two methods are not just slightly disagreeing, they are telling fundamentally different stories about the universe. For years, many scientists hoped the tension would simply resolve itself. Perhaps there was a systematic error in one of the measurements. Perhaps the Cepheid stars were not as reliable as assumed. Perhaps the cosmic microwave background analysis was missing something. Uncomfortable, but not impossible. One side of the equation might have a hidden flaw. Then Webb arrived. One of the first major scientific programs undertaken with Webb was a direct effort to resolve the Hubble tension, to use its vastly superior resolution and sensitivity to check the Cepheid measurements more carefully than ever before. The team was led by Nobel Prize-winning astronomer Adam Rees, one of the scientists who originally discovered that the expansion of the universe is accelerating. If anyone was equipped to find the error and close the gap, it was him. Webb looked at the Cepheid stars with unprecedented clarity. It separated them from neighbouring stars that previous telescopes couldn't resolve. It removed potential sources of contamination. It performed the most careful, precise measurement of these stellar distances ever attempted. And the answer came back 73, not 67, not somewhere in between. The distance ladder, measured with the most powerful telescope ever built, still pointed firmly to 73. The Cepheid measurements were not wrong. The error, if there was one, was not there, which means the tension is real, which means our two most reliable methods for measuring the expansion rate of the universe are genuinely, irreconcilably disagreeing with each other. And that is not a measurement problem. That is a physics problem. Somewhere in our understanding of the cosmos, in our models, in our assumptions, in the equations we use to describe how the universe behaves, something is missing, or something is wrong. And Webb, rather than resolving the mystery, has made it sharper, cleaner, and impossible to look away from. There is something deeply human about the discomfort of not knowing. We build models, we construct frameworks, we draw maps of things we cannot see with our own eyes, maps of the early universe, maps of the expansion of space, maps of forces and particles and fields that exist far beyond the reach of ordinary perception. And we do this not just because it is useful, but because it makes us feel oriented. It gives us the sense that the universe is a place we can understand, a place that follows rules we can discover, a place that will eventually yield its secrets to a persistent enough mind. And then something like the Hubble tension comes along and reminds us that the map is not the territory. But here is what is important to understand. And this is something that often gets lost when science communicates its uncertainties to the wider world. The fact that our models are breaking down is not a failure. It is not a sign that science doesn't work, or that we have been doing something wrong all along. It is in fact the exact opposite. It is science working precisely as it is supposed to work. Every great leap in our understanding of the universe has been preceded by exactly this kind of tension, by numbers that didn't add up, by observations that refused to fit into existing frameworks, by the uncomfortable feeling that something fundamental had been missed. At the end of the 19th century, physicists were quietly confident that they had more or less figured out the basic laws of nature. Classical mechanics, thermodynamics, electromagnetism, the edifice of physics seemed nearly complete. There were just a few small loose ends to tie up. One of them was a puzzling problem called the ultraviolet catastrophe. The fact that classical theory predicted that a heated object should emit infinite energy at short wavelengths, which was obviously not what happened in reality. That small loose end unravelled everything. The attempt to solve it gave birth to quantum mechanics, one of the two pillars of modern physics, a framework so strange and counterintuitive that even its founders spent years arguing about what it actually meant. Another loose end was the fact that the speed of light appeared to be constant regardless of the motion of the observer, which contradicted everything classical mechanics said should be true. Einstein pulled on that thread and produced special relativity, then general relativity, rewriting our entire understanding of space, time, and gravity. The loose ends were the most important parts. What Webb is showing us now might be exactly that kind of loose end. The Hubble tension, the impossibly massive early galaxies. These are not just minor inconveniences to be smoothed over with a small correction factor. They are persistent, stubborn, replicable anomalies that point towards something our current physics does not contain. And the scientific community, to its credit, is not ignoring them. Across universities and research institutes around the world, theorists are working on possible explanations. Some are conservative, small modifications to existing models, tweaks that might bring the numbers back into alignment without requiring any dramatic revision of our fundamental picture. Others are far more radical. They involve entirely new components of the universe that we have never directly detected, new forms of energy, new particles, new interactions between things we thought we understood. One of the most discussed possibilities involves something called early dark energy. Dark energy is already one of the strangest things in modern cosmology. It is the name we give to whatever is causing the expansion of the universe to accelerate, a force or field or property of space itself that pushes outward against gravity, driving galaxies apart at an ever-increasing rate. It was discovered in 1998, won the Nobel Prize in 2011, and remains almost entirely mysterious. We know it exists because we can measure its effects. We have essentially no idea what it actually is. Early dark energy is a proposed variation on this theme. The idea is that in the very early universe, in the first few 100,000 years after the Big Bang, there was an additional component of dark energy that was active then but has since faded away. If this early dark energy existed, it would have affected the expansion rate of the young universe in ways that could potentially shift the value predicted from the cosmic microwave background closer to the value measured by the distance ladder. It is an elegant idea. It is also, so far, unconfirmed. And some analyses of Webb's data suggest that even early dark energy may not be enough to fully bridge the gap. Which brings us to the more radical possibilities, the ones that don't just add a new ingredient to the existing recipe, but question whether the recipe itself is correct. Let's talk about dark matter. Not because it solves the problems Webb has uncovered, it doesn't, at least not directly, but because understanding dark matter is essential to understanding just how deep the strangeness goes, and because the story of dark matter is, in its own right, one of the most extraordinary detective stories in the history of science. It begins in the 1930s with a Swiss astronomer named Fritz Zwicky, who had a reputation for being both brilliant and extraordinarily difficult to get along with. Zwicky was studying a cluster of galaxies called the Coma Cluster, a dense collection of hundreds of galaxies bound together by gravity. He measured the velocities of individual galaxies within the cluster, and then he did a simple calculation. If you know how fast the galaxies in a cluster are moving, and you know how much mass is there, mass you can estimate by measuring how bright the cluster is, you can calculate whether the cluster should be holding together or flying apart. It's a straightforward application of gravitational physics. The numbers didn't work. The galaxies in the Coma Cluster were moving far too fast to be held together by the visible matter alone. Based on the light the cluster emitted, there simply wasn't enough mass to generate the gravity needed to keep everything bound. The cluster should have been tearing itself apart, and yet there it was, stable, coherent, holding together. Zwicky's conclusion was that there must be additional mass present that was not visible, mass that didn't emit light, did not absorb light, didn't interact with electromagnetic radiation in any detectable way, mass that made its presence known only through gravity. He called it dunkel Materie, dark matter. For decades, Zwicky's idea was treated with skepticism. It was too strange, too radical, too convenient. A way of making the math work by invoking something invisible and undetectable. But the evidence kept accumulating. In the 1970s, astronomer Vera Rubin measured the rotation curves of spiral galaxies, the speeds at which stars orbit around the galactic center at different distances, and found the same problems Zwicky had found, now appearing at the scale of individual galaxies. Stars at the outer edges of galaxies were moving far faster than they should given the visible mass. Again, there was too much motion for too little matter. The pattern was undeniable, and it pointed to the same conclusion. There is something out there that we cannot see, something that has mass and therefore gravity, something that is distributed throughout and around galaxies in vast invisible halos, and we have no idea what it is. Today, the best estimates suggest that ordinary matter, the stuff made of protons, neutrons and electrons, the stuff that makes up stars, planets, gas clouds, and every atom in your body, accounts for only about 5% of the total mass energy content of the universe. Dark matter accounts for roughly 27%, and dark energy, that mysterious accelerating force, accounts for the remaining 68%, 5%. Everything we have ever seen, touched, studied, or built instruments to detect, all of it together, is just 5% of what the universe actually contains. The other 95% is invisible to us. We know it's there. We can measure its effects. And we cannot directly detect a single particle of it. This is the universe we live in. And now Webb is telling us that even our understanding of that 5%, the ordinary matter, the stars, the galaxies, the things we can actually see, might be more incomplete than we realized. Because those massive early galaxies don't just challenge our models of galaxy formation. They challenge our models of how dark matter behaves in the early universe. They challenge our understanding of how quickly matter, dark and ordinary alike, can clump together under gravity and build the enormous structures we are now observing. Some theorists have begun asking a question that would have seemed almost unthinkable a few years ago. What if our model of dark matter itself needs to be revised? What if dark matter doesn't behave exactly the way we assumed? What if it has properties, interactions, or behaviors that our standard model doesn't account for? And a smaller but growing number of voices are asking something even more radical. What if dark matter, as we currently conceive of it, doesn't exist at all? The idea that dark matter might not exist is not new. It has been circulating at the edges of mainstream cosmology for decades, proposed by researchers who looked at the same anomalies everyone else was looking at, and decided to pull on a different thread. Instead of adding invisible matter to make the equations balance, they asked a different question. What if the equations themselves are wrong? What if gravity, the force we think we understand better than almost any other, doesn't behave exactly the way we think it does at very large scales? The most developed version of this idea is called MOND, which stands for Modified Newtonian Dynamics. It was proposed in 1983 by Israeli physicist Mordechai Milgram, and the core idea is surprisingly simple. In our everyday experience, and at the scales we can test in laboratories and solar systems, Newton's law of gravity works perfectly. The gravitational force between two objects is proportional to their masses and inversely proportional to the square of the distance between them. Clean, precise, testable. Milgram noticed something curious about the galaxy rotation problem that Vera Rubin had uncovered. The discrepancy between observed and predicted star velocities didn't appear uniformly throughout galaxies. It became significant specifically in regions where the gravitational acceleration was extremely low, and he proposed that perhaps, below a certain threshold of acceleration, gravity behaves slightly differently than Newton's law predicts. Not dramatically differently, just enough to account for the extra velocity without needing any invisible matter. For certain specific observations, MOND works remarkably well. It predicts galaxy rotation curves with impressive accuracy across a wide range of galaxy types. It makes predictions about the relationship between a galaxy's visible mass and its rotation speed that have been repeatedly confirmed by observation. These are genuine successes, and they are not trivial. But MOND has serious problems at larger scales. It struggles to explain the behavior of galaxy clusters, the very phenomenon that led Zwicky to propose dark matter in the first place. It has difficulty accounting for the pattern of fluctuations in the cosmic microwave background, and in its original form, it is not a relativistic theory, meaning it cannot be fully integrated with general relativity, which is our best description of gravity at cosmological scales. Various attempts have been made to extend MOND into a more complete relativistic framework. The most prominent is a theory called TVES, tensor vector scalar gravity, developed by physicist Jacob Bekenstein. But TVES and its successors have their own problems, and none of them has managed to fully replace the explanatory power of the dark matter model across all observations simultaneously. So, where does that leave us? In a genuinely uncomfortable place. Dark matter explains a lot, but we have never detected it directly, despite decades of increasingly sensitive experiments designed specifically to catch it. Modified gravity explains some things remarkably well, but it fails in other areas where dark matter succeeds. Neither framework is complete, neither framework is fully satisfying, and Webb is not resolving this tension, it is deepening it. Because some of the early massive galaxies that Webb has found are difficult to explain even with our standard dark matter model. The standard model predicts that dark matter halos, the invisible scaffolding around which galaxies form, should grow gradually over time, slowly accumulating mass through mergers and accretion. Large halos, capable of hosting large galaxies, should take billions of years to assemble. But some of the galaxies Webb is finding appear to be sitting in halos that are already enormous at a time when they shouldn't be. The scaffolding is already built. The construction happened faster than the model allows. Some researchers have proposed that this could be explained by tweaking the properties of dark matter, making it behave slightly differently in the early universe than in the late universe. Others have proposed entirely new varieties of dark matter with different interaction properties. Still others are looking at the problem from a completely different angle, questioning not the dark matter model, but our understanding of how stars form within dark matter halos and whether the efficiency of star formation in the early universe could have been dramatically higher than we currently assume. Every proposed solution opens new questions. Every answer reveals a deeper layer of uncertainty. And through it all, Webb keeps looking, keeps sending back images and spectra and data points that don't fit neatly into any of the existing boxes. It is, depending on how you look at it, either deeply frustrating or deeply thrilling, and perhaps it is both at once. Let's step back for a moment from the technical details and sit with something larger. We have been talking about numbers and models and tensions in the data, Hubble constants and galaxy masses and dark matter halos and modified gravity, and all of that is real and important and worth understanding. But underneath all of it, there is something more fundamental happening, something that goes beyond any specific measurement or any particular anomaly. What Webb is doing, in the deepest sense, is expanding the boundary of the known, and every time that boundary expands, the unknown expands with it. This is one of the most counterintuitive things about scientific progress, and it is something that surprises people when they first really grasp it. You might expect that as we learn more, the territory of the unknown shrinks. That knowledge is a light that, as it grows brighter, illuminates more and more of the darkness until eventually everything is visible. And in some narrow sense, that is true. We know more about the universe today than we did 50 years ago. We know vastly more than we did a century ago. But the deeper truth is that knowledge also reveals the shape of our ignorance. Before you know enough to ask the right question, you don't even know what you don't know. You're standing in a dark room, and the darkness feels complete. Not because the room is empty, but because you cannot see its walls. The moment someone turns on a light, you realize the room is much larger than you imagined, and you can see, for the first time, all the doors you didn't know were there. Webb has turned on a light in a room that humanity has been standing in for its entire existence, and the room is larger than we thought. The walls are further away than our best measurements suggested, and there are doors, many doors, that we didn't know existed and cannot yet open. This is worth sitting with quietly for a moment. Think about what it means to live at this particular point in history. For tens of thousands of years, human beings looked up at the night sky and saw the same thing you see tonight. Stars, the moon, the faint band of the Milky Way, and had no framework to understand what any of it was. No concept of galaxies, no understanding of cosmic distances, no way of knowing that the light reaching their eyes had travelled for millions or billions of years. The universe was a mystery in the most complete sense. Not a mystery with known edges, but a mystery without any map at all. We have come an extraordinary distance from that starting point. We have measured the age of the universe to within a small margin of error. We have mapped the large-scale structure of the cosmos, the way galaxies cluster into filaments and sheets and voids across billions of light years. We have detected gravitational waves, ripples in the fabric of space-time produced by colliding black holes and neutron stars, confirming predictions that Einstein made more than a century ago without ever imagining they could be tested. We have found thousands of planets orbiting other stars, including some that might, under the right conditions, harbour liquid water. We have done all of this with instruments built by human hands, based on ideas developed by human minds, in a cosmic eye blink of time. And now Webb is showing us that even this extraordinary edifice of knowledge, all of it, is built on a foundation that has cracks we didn't fully appreciate before. Not cracks that make the building collapse, but cracks that reveal there is more building to do. More foundation to pour, more structure to raise above what we have already constructed. The universe is not just larger than we thought, it is stranger than we thought. And it is stranger in ways that are specific, measurable, and pointing in directions that our current physics cannot yet fully follow. That strangeness is not a problem to be embarrassed about. It is an invitation. It is the universe doing what it has always done, thus being more than we expected, exceeding our models, refusing to be fully contained by the frameworks we build to describe it. And Webb, floating in the cold darkness 1.5 million kilometres from home, golden mirrors tilted toward the deep past, is our most precise instrument for reading that invitation. There is a specific image that Webb captured in the summer of 2022 that stopped people in their tracks. It was released on July 12th of that year, during a presentation at the White House, an unusual venue for an astronomical image, but perhaps an appropriate one given what it showed. The image was called Webb's First Deep Field. It covered a patch of sky so small that, held at arm's length, it would be hidden behind a grain of sand. And within that grain of sand-sized patch of sky, there were thousands of galaxies. Thousands. Some of them sharp and bright in the foreground. Some of them smeared into arcs and streaks by the gravitational pull of a massive galaxy cluster sitting between them and us, a phenomenon called gravitational lensing, where the mass of an intervening object bends the light passing around it, distorting and magnifying the sources behind it like a cosmic magnifying glass. And some of them so faint, so ancient, so impossibly distant that they appeared as nothing more than the faintest smudges of reddish light at the very edge of visibility, light that had been travelling toward us for more than 13 billion years. People who saw that image and understood what they were looking at often described a particular sensation. Not just awe, though there was certainly awe. Something more specific than that. A kind of vertiginous shift in scale. The feeling of suddenly perceiving, in a visceral rather than merely intellectual way, just how vast the universe actually is. Just how many galaxies there are. Just how many stars. Just how many possible worlds. Carl Sagan once wrote that the universe is not required to be in perfect harmony with human ambition. It is a line worth remembering when you look at an image like Webb's First Deep Field, because the universe visible in that image, infinite in its apparent depth, indifferent in its scale, ancient beyond any meaningful human analogy, has no particular concern for what we expected to find there. It simply is what it is. And what it is, Webb is now showing us, is something more complicated and more surprising than we had prepared ourselves for. Among the thousands of galaxies in that first deep field image, and in the many deep field observations that followed, researchers began identifying objects that match the profile of the anomalously massive early galaxies, the ones that shouldn't be there yet, the ones that the models couldn't account for. Each identification required careful, follow-up spectroscopy, a technique that spreads the light from a galaxy into its component wavelengths, producing a spectrum that reveals the galaxy's redshift with precision, and with it, its true distance, and the true age of the universe when its light was emitted. The spectroscopic confirmations came back, one after another. The galaxies were real. The distances were real. The masses estimated from the brightness and colour of the light were real, or at least consistent with being real, within the uncertainties involved. And the conversation within the scientific community began to shift from cautious skepticism to something more like serious reckoning. What exactly would it take to form a galaxy of hundreds of billions of solar masses within the first few 100 million years of the universe? What conditions would need to exist? What physics would need to operate? The answers, when researchers tried to work them out, kept pointing in uncomfortable directions. Either the efficiency of star formation in the early universe was dramatically higher than anything our models predict, high enough that it would require some currently unknown mechanism to explain, or there is something wrong with our understanding of the early universe itself, its density, its structure, the way matter was distributed in those first moments after the Big Bang, or both. One possibility that has gained some traction is that the initial conditions of the universe, the tiny fluctuations in density that seeded all subsequent structure, were not quite what our standard model of inflation predicts. Inflation is the theory that the universe underwent a period of extraordinarily rapid exponential expansion in the first tiny fraction of a second after the Big Bang, smoothing out irregularities and setting up the conditions for all subsequent structure formation. It is a powerful and widely accepted theory, but its details remain uncertain, and different variants of inflationary theory predict slightly different patterns of initial fluctuations. If the initial fluctuations were somewhat larger or more concentrated than the standard prediction, structure could have begun forming earlier and more efficiently, potentially explaining at least some of what Webb is finding, but only some. The most extreme of the early massive galaxies remain difficult to explain even with generous modifications to the initial conditions, and that is what keeps theorists awake at night. Not the cases that can be explained with a small adjustment, but the ones that resist every adjustment and simply sit there in the data, patient and immovable, waiting for an explanation that has not yet arrived. By now you might be wondering about something. All of this, the massive early galaxies, the Hubble tension, the questions about dark matter and modified gravity, rests on one critical assumption. It rests on our ability to accurately measure distances in the universe, to know how far away these galaxies actually are, to correctly interpret the redshift of their light as a measure of cosmic distance and cosmic time. What if that assumption has a flaw? It is a question worth taking seriously, because if our distance measurements are systematically off, if there is some error in the way we convert redshift into distance and age, then some of the anomalies Webb has uncovered might dissolve. The galaxies might not be as ancient as we think, or not as massive, or both. The standard interpretation of redshift as a measure of cosmic expansion rests on extremely well-tested physics. The relationship between redshift and distance, Hubble's law, has been confirmed by multiple independent methods across a huge range of distances. Gravitational lensing, the cosmic microwave background, baryon acoustic oscillations. These are all independent probes of cosmic geometry that all tell a consistent story about the large-scale structure of the universe. It is very difficult to construct a coherent alternative interpretation that preserves all of these consistencies while also explaining away the anomalies. Researchers have tried so-called tired light theories, the idea that light loses energy over distance for some reason other than cosmic expansion, mimicking a redshift without implying an expanding universe, have been around since the 1920s and have never been able to explain the full range of observations that the standard model handles naturally. So the distances are almost certainly real, the ages are almost certainly real, and the problem is almost certainly real. But there is another layer of uncertainty worth acknowledging, and it has to do with mass estimation. When astronomers look at a distant galaxy and estimate its mass, they are not weighing it directly. They are measuring its light, its brightness, its colour, the spectrum of wavelengths it emits, and using that information to infer how many stars it contains and how massive those stars are. This inference relies on what are called stellar population models, mathematical frameworks that predict what a given mix of stars of different ages and compositions should look like in terms of the light they emit. These models are sophisticated and well tested on nearby galaxies, but there is a genuine question about how well they apply to galaxies in the very early universe, where the first generations of stars may have been dramatically different from the stars we observe today. The very first stars, called population 3 stars, formed from gas that contained almost no elements heavier than hydrogen and helium, because heavier elements had not yet been produced in stellar interiors. These stars are predicted to have been extremely massive, extremely hot, and extremely short-lived. They would have emitted light with a very different spectrum than later stellar generations. If the massive early galaxies Webb is observing contain large populations of these exotic early stars, or stars with unusual properties that our current models don't fully capture, then our mass estimates might be too high. The galaxies might be somewhat less massive than the data suggests. Somewhat. But probably not by enough to make the problem disappear entirely. Even conservative estimates of the masses of the most extreme early galaxies leave them well above what standard models predict should be possible at those epochs. So the problem remains, softened perhaps at the edges but solid at the core. And Webb is not done looking. It has years of observations ahead of it, years of data that will either deepen the anomalies or begin to resolve them in ways we cannot yet predict. Every new observation is a new piece of evidence in a case that is still very much open. The universe has given us a puzzle, and we're only beginning to understand its shape. There is something Webb found that we haven't talked about yet, something that, in some ways, is even more disorienting than the massive early galaxies or the Hubble tension. Something that doesn't just challenge our models of how the universe evolved, it challenges our assumptions about what the universe is made of at the most fundamental level. It has to do with the chemical composition of the early universe. When the Big Bang occurred, the universe was initially too hot and too dense for any atoms to exist. In the first fractions of a second, it was a seething plasma of quarks and gluons, the fundamental building blocks of matter, interacting at energies so extreme that the particles we know today couldn't yet form. As the universe expanded and cooled, quarks bound together into protons and neutrons. And then, in the first few minutes after the Big Bang, a period cosmologists call Big Bang nucleosynthesis. Those protons and neutrons combine to form the first atomic nuclei. The physics of this process is extremely well understood. The conditions of the early universe, the temperature, the density, the ratio of protons to neutrons, can be calculated with precision, and they predict with great accuracy what proportions of different light elements should have been produced. The prediction is approximately 75% hydrogen, 25% helium, and trace amounts of lithium and a handful of other light elements. This is called the primordial abundance, and for hydrogen and helium, the predictions match observations beautifully. The early universe, as best we can measure, was indeed about 75% hydrogen and 25% helium. This agreement is one of the great successes of the Big Bang model, a precise quantitative prediction confirmed by independent measurements. But lithium tells a different story. The predicted abundance of lithium-7, the most common isotope of lithium produced in Big Bang nuclear synthesis, is significantly higher than what is actually observed in the oldest stars we can study. Stars that formed very early in cosmic history, from gas that should still reflect the primordial composition, consistently show lithium abundances that are about 3 times lower than the theory predicts. This discrepancy has been known for decades. It is called the cosmological lithium problem, and despite decades of effort, it has never been satisfactorily resolved. Various explanations have been proposed. Perhaps the old stars have processed some of their lithium through nuclear reactions in their interiors, depleting the surface abundance. Perhaps there are systematic errors in the stellar atmosphere models used to infer the lithium content. Perhaps some unknown nuclear physics process destroyed lithium in the early universe before it could be incorporated into stars. None of these explanations has been fully convincing. The lithium problem sits in the literature like a splinter, too small to demand immediate attention, too persistent to be ignored. And now Webb is giving us the tools to study the chemical composition of the early universe with a precision that was previously impossible. By observing the spectra of very distant, very ancient galaxies, and of the rare surviving stars from the earliest epochs that still exist within our own galaxy, Webb can measure elemental abundances with extraordinary sensitivity. What it is finding is adding new complexity to an already complex picture. The chemical evolution of the early universe, the way elements were produced, distributed, and incorporated into successive generations of stars and galaxies, appears to have proceeded faster and in ways more varied than our models predict. Heavy elements, which can only be produced inside stars and distributed through stellar explosions, are appearing in some early galaxies at levels that suggest those galaxies have already gone through multiple generations of star formation by a time when, according to our models, they should barely have begun their first. The universe, it seems, was a more efficient chemist than we gave it credit for, and that efficiency points again towards something happening in the early universe that our current models are not capturing. Let's talk about black holes, not the ones we usually talk about. The stellar mass black holes formed when massive stars collapse at the end of their lives, or even the somewhat larger ones that merge and produce the gravitational waves that detectors like LIGO have been measuring since 2015. Let's talk about the ones that sit at the centres of galaxies, the ones called supermassive black holes. Every large galaxy we know of appears to host a supermassive black hole at its centre. Our own Milky Way has one. It's called Sagittarius A star, and it has a mass of about 4 million times the mass of our Sun. The galaxy M87, famously imaged by the Event Horizon Telescope in 2019, has a central black hole of about 6.5 billion solar masses. These are objects of almost incomprehensible density, volumes of space from which not even light can escape, surrounded by swirling disks of superheated matter that can outshine entire galaxies when actively feeding. We know these objects exist. We've imaged them directly. We have watched stars orbit around the one at the centre of our own galaxy for decades, their paths tracing the invisible gravitational grip of something 4 million times more massive than the Sun packed into a region smaller than our solar system. What we don't fully understand is how they got so big. The standard picture of supermassive black hole formation involves a long process of gradual growth. A black hole forms, perhaps from the collapse of a massive early star, or from the direct collapse of a dense cloud of gas, and then grows over billions of years by accreting matter from its surroundings and merging with other black holes. This is a slow process. There are physical limits on how fast a black hole can accrete matter, a limit called the Eddington limit, set by the radiation pressure of the infalling material pushing back against further accretion. Given these limits, forming a black hole of billions of solar masses should take a very long time. Billions of years, in fact. And yet Webb is finding evidence of supermassive black holes, objects of hundreds of millions or even billions of solar masses, already in place in the very early universe, in galaxies that existed when the universe was only a few 100 million years old. Black holes that, according to our standard model of their growth, simply should not be that large that soon. This is the black hole version of the same problem we saw with the galaxies themselves. Too big, too early, too massive, too soon. The universe apparently didn't consult our growth models before assembling its larger structures. One proposed solution involves what are called direct collapse black holes. Instead of forming from a stellar collapse and growing slowly, these hypothetical objects would form directly from the collapse of enormous clouds of primordial gas. Clouds so massive and so dense that they skip the star formation stage entirely and collapse straight into a black hole of 100,000 or even 1,000,000 solar masses from the very beginning. This would give them a much larger starting mass, and therefore a much shorter time needed to reach billions of solar masses through subsequent accretion. Direct collapse black holes are theoretically plausible, but they require very specific conditions that are difficult to produce in standard cosmological models, and they have never been directly observed. Webb is currently one of our best hopes for finding them, or finding evidence that they existed in the early universe. Some candidate objects have already been identified in Webb's data, sources that appear to be extremely massive black holes in very young galaxies, without the surrounding stellar population you would expect if the black hole had grown through the standard route. These candidates are still being analysed, still being debated, still being subject to the careful scrutiny that extraordinary claims require. But they are there, in the data, waiting for an explanation, and the explanation, when it comes, will tell us something profound about the earliest moments of cosmic history, about what happened in the universe's infancy, in that deep darkness before the first stars turned on and light began to move freely through space for the first time. That moment, the moment when the universe became transparent to light, is called the epoch of reionization. And it is the next frontier that Webb is pushing into, one observation at a time, one ancient photon at a time, reaching back toward the edge of the knowable universe, with its golden mirrors and its extraordinary patience. The epoch of reionization is one of the most evocative phrases in all of cosmology. It sounds technical, and in one sense it is. But what it describes is something that, once you understand it, feels almost mythological in its scale and drama. It is the story of how the universe went from darkness to light, not metaphorically, but literally, a transition that took hundreds of millions of years and reshaped the entire cosmos in the process. Here is what happened. In the first few 100,000 years after the Big Bang, the universe was so hot and so dense that electrons and protons couldn't combine to form neutral hydrogen atoms. The universe was essentially a plasma, a fog of charged particles so thick that photons, particles of light, couldn't travel freely through it. They were constantly scattering off the free electrons, bouncing around, unable to move in straight lines. The universe was not just dark in the sense of having no light sources. It was opaque. Light existed, but it couldn't go anywhere. Then, around 380,000 years after the Big Bang, the universe had expanded and cooled enough that electrons and protons could finally combine. Neutral hydrogen atoms formed for the first time, and with the free electrons suddenly bound up inside atoms, the fog lifted. Photons were finally free to travel in straight lines across the universe. That moment of liberation, called recombination, somewhat confusingly, since the electrons and protons were combining for the first time rather than recombining, produced the light we now detect as the cosmic microwave background. It is the oldest light in the universe, the furthest back we can see using electromagnetic radiation of any kind. A snapshot of the universe at 380,000 years old, preserved across 13.8 billion years and still washing over us today from every direction. But after recombination, the universe entered what cosmologists call the Dark Ages. Not a metaphor this time. The universe was literally dark. There were no stars yet. There were no galaxies yet. There was only hydrogen and helium gas, slowly cooling, slowly clumping together under the influence of gravity and the invisible scaffolding of dark matter. For hundreds of millions of years, the universe was a cold, dark, almost featureless expanse of gas, punctuated only by the subtle variations in density that would eventually seed the first structures. And then, somewhere in that darkness, the first stars turned on. The details of exactly when and how this happened are still uncertain. It is one of the central questions that Webb was designed to help answer. But at some point, probably between 100 and 300 million years after the Big Bang, gravity had pulled enough gas together into dense enough concentrations that nuclear fusion ignited at the core. The first star blazed into existence, and then another, and then another. These first stars, population 3 stars as astronomers call them, were almost certainly very different from the stars we know today. Formed from gas that was almost pure hydrogen and helium, without any of the heavier elements that influenced star formation in later epochs. They are predicted to have been enormously massive, perhaps hundreds of times the mass of our Sun, and correspondingly brilliant, hot and short-lived. They would have burned through their fuel in just a few million years, ending their lives in titanic explosions that scattered the first heavy elements into the surrounding gas. And they would have done something else. They would have begun ionizing the hydrogen gas around them, stripping electrons away from atoms with their intense ultraviolet radiation, reversing the process of recombination that had occurred hundreds of millions of years earlier. This is reionization, the process by which the first stars and eventually the first galaxies gradually converted the neutral hydrogen of the cosmic dark ages back into a plasma of free electrons and protons. It was not instantaneous. It took hundreds of millions of years, spreading outward from the first luminous sources like bubbles of ionized gas growing and merging in a sea of neutral hydrogen, until finally, around 1 billion years after the Big Bang, the process was complete. The universe was fully ionized. It was transparent to ultraviolet light. And the modern universe, the one of stars and galaxies and quasars and planets, was underway. Webb is now peering directly into this epoch. And what it is finding is already beginning to reshape our understanding of how reionization actually happened. One of the things Webb has been doing, quietly and systematically, is measuring the properties of galaxies during the epoch of reionization with a precision that was simply not possible before. And one result in particular has caught the attention of the community. The sources of reionization, the objects that produce the ultraviolet photons that ionize the cosmic hydrogen, have long been debated. The leading candidates were always galaxies, specifically the young star-forming galaxies of the early universe, whose hot young stars produce copious amounts of ionizing radiation. But there was always a question of whether galaxies alone were sufficient, or whether other sources, quasars for instance, the brilliantly luminous cores of galaxies powered by actively feeding supermassive black holes, needed to contribute significantly. Webb has been measuring something called the ionizing photon escape fraction, the proportion of ionizing photons produced inside a galaxy that actually manage to escape into the surrounding intergalactic medium, rather than being absorbed by gas and dust within the galaxy itself. This is a critical parameter. If photons can't escape the galaxy, they can't ionize the surrounding universe. Previous observations suggested that escape fractions were generally quite low, only a few %, meaning that only a small fraction of the ionizing radiation produced inside galaxies actually made it out. This made it difficult to account for reionization using galaxies alone, and led some researchers to invoke quasars as important contributors. Webb is finding escape fractions that are, in at least some early galaxies, significantly higher than expected. Some young, compact, intensely star-forming galaxies in the reionization epoch appear to be leaking ionizing photons at rates that are dramatically higher than what previous models assumed. This changes the accounting. If enough early galaxies were efficient leakers of ionizing radiation, galaxies alone might be sufficient to explain reionization without needing a significant contribution from quasars. This is not a settled question. There is still significant debate, and the sample sizes are still relatively small. But it illustrates something important about how Webb is changing the field, not just by revealing unexpected objects or unexpected structures, but by measuring familiar phenomena with a precision that changes the quantitative conclusions we draw from them. Precision matters enormously in cosmology. Small changes in measured quantities can have large implications for the models we build. A factor of 2 change in the ionizing photon escape fraction might seem like a minor technical detail, but it ripples outward through the entire framework of reionization physics, changing timelines, changing the relative contributions of different source populations, changing our picture of how the universe transitioned from its dark ages to its current luminous state. Webb is full of these precision measurements, full of small numbers that shift by amounts that seem modest but carry enormous implications, and they are accumulating, building up into a picture of the early universe that is both more detailed and more puzzling than what we had before. There is a concept in science called a paradigm shift, a phrase coined by philosopher Thomas Kuhn to describe those moments when the accumulation of anomalies becomes too great for the existing framework to absorb, and the entire framework is replaced by a new one. Kuhn argued that science doesn't progress purely through gradual accumulation of knowledge. It progresses through revolutions, sudden reorganizations of understanding that reframe everything that came before. We may not be at a paradigm shift yet. Most cosmologists would say we are not. That the anomalies Webb has uncovered are real and important, but not yet sufficient to require a wholesale replacement of the standard cosmological model. The model is wounded, they would say, but not broken. It needs revision, not replacement. But some researchers are less certain. Some are looking at the accumulation of tensions, the Hubble tension, the massive early galaxies, the oversized early black holes, the unexpected chemical abundances, the higher-than-expected escape fractions, and seeing not a collection of isolated puzzles, but a pattern that suggests something more fundamental is missing from our understanding, something that, when it is eventually identified, will not just patch the existing model but transform it. History suggests they might be right. History suggests that the most important discoveries in science often arrive not as triumphant confirmations of existing ideas, but as persistent, uncomfortable failures of expectation, as numbers that don't add up, as observations that refuse to behave, as exactly the kind of thing Webb keeps finding every time it opens its golden eye and looks a little deeper into the dark. There is a question that has been hovering at the edge of everything we have discussed so far, and it is time to bring it closer. If the universe is not behaving the way our models predict, if galaxies are forming too fast, if the expansion rate doesn't agree with itself, if black holes are growing too quickly and chemical elements are appearing too soon, then what exactly is wrong? Where is the error? Is it in the data? Is it in the models? Is it in the fundamental assumptions we have been carrying for decades without examining closely enough? These are not rhetorical questions. They are the actual questions that cosmologists are sitting with right now, in offices and observatories and late-night conversations over conference room tables. And the honest answer, the answer that the most careful and intellectually rigorous scientist will give you, is that we don't know yet. But there are directions. There are threads being pulled. And some of them lead to places that are genuinely extraordinary. One of the most radical directions involves revisiting something that sits at the very foundation of modern cosmology, something so fundamental that most physicists treat it not as an assumption, but as an established fact. It is called the cosmological principle. The cosmological principle states that the universe, when viewed at sufficiently large scales, is homogeneous and isotropic. Homogeneous means that it looks the same from every location, no special places, no centers, no edges. Isotropic means that it looks the same in every direction, no preferred axis, no large-scale asymmetries. Put simply, the universe is, on average, uniform. This principle is not just a convenience. It is the load-bearing wall of the entire standard cosmological model. Without it, the equations that describe cosmic evolution become vastly more complicated, essentially unsolvable in their full generality. The cosmological principle allows us to simplify those equations dramatically, to make predictions that can be tested against observations, to build the framework we call the lambda-CDM model, the standard model of cosmology that has been so successful for so long. But what if it isn't exactly right? What if the universe, at scales even larger than we have been able to measure, is not perfectly uniform? What if there are structures, vast subtle inhomogeneities, that extend beyond our current observational horizon and influence the expansion rate, the formation of structure, and other cosmological observables in ways we haven't accounted for? This idea goes by various names in the literature. One of the most developed versions is called the Hubble bubble hypothesis, the idea that we might be living inside a large underdense region of the universe, a void where the local expansion rate is slightly higher than the global average. If the local density of matter is lower than average, local gravity is weaker and the local expansion is faster. This would cause distance ladder measurements, which sample the relatively nearby universe, to give a higher value for the Hubble constant than measurements based on the cosmic microwave background, which samples the entire observable universe. The difference between 67 and 73 kilometers per second per megaparsec, the Hubble tension, could potentially be explained, at least in part, by exactly this kind of large-scale structure effect. Some observations do suggest that we may live in a region of below-average density. Analyses of galaxy surveys have found tentative evidence for a local underdensity on scales of hundreds of millions of light-years. But the evidence is not conclusive, and the underdensity, even if real, may not be large enough to fully account for the tension. And if it turns out that the cosmological principle itself needs revision, if the universe is genuinely inhomogeneous at scales we haven't yet mapped, the implications extend far beyond the Hubble tension. They reach into the foundations of how we model cosmic evolution, how we interpret the cosmic microwave background, how we estimate the age of the universe, and how we understand the large-scale geometry of space itself. It is a thread that, if pulled hard enough, could unravel a very large portion of the fabric. But let's go even deeper. Because there is another possibility, one that sits at the intersection of cosmology and fundamental physics, and that has been gaining quiet attention in recent years. It doesn't just question our model of the universe, it questions our model of space and time themselves. General relativity, Einstein's theory of gravity published in 1915, is one of the most precisely tested theories in the history of science. It has passed every experimental test thrown at it, from the bending of light around massive objects to the precise timing of signals from pulsars to the detection of gravitational waves exactly as predicted. It is by any measure an extraordinary intellectual achievement and a remarkably accurate description of how gravity works. But general relativity has a problem. It doesn't get along with quantum mechanics. Quantum mechanics, the theory that describes the behavior of matter and energy at the smallest scales, is equally well tested, equally precise, equally successful within its domain, and the two theories are fundamentally incompatible. They use different mathematical frameworks, different conceptual foundations, different ways of describing reality. In the regimes where each theory individually applies, large scales for general relativity, small scales for quantum mechanics, both work beautifully. But in regimes where both should apply simultaneously, at the centre of black holes, at the very beginning of the universe, they produce contradictions and infinities that signal a breakdown of understanding. Physicists have known about this incompatibility for nearly a century, and for nearly a century they have been trying to resolve it, to find a unified theory that reduces to general relativity at large scales, and to quantum mechanics at small scales, while remaining coherent and consistent at all scales. This effort has produced some of the most creative and ambitious theoretical physics ever attempted. String theory, the idea that the fundamental constituents of reality are not point-like particles, but tiny one-dimensional vibrating strings, has been developed for decades and involves mathematics of extraordinary sophistication. Loop quantum gravity, an alternative approach that attempts to quantize space-time itself, treating it as a discrete network of loops rather than a smooth continuum, has produced its own rich body of theory. Various other approaches with names like causal dynamical triangulation, asymptotic safety, and causal set theory each attack the problem from different angles. None of them has yet produced a confirmed, tested prediction that distinguishes it from general relativity in a regime accessible to current experiments. None of them has been proven, and several of them make predictions about the very early universe, about what happened at and before the Big Bang, about the nature of inflation, about the initial conditions that seeded all subsequent structure that differ subtly from the standard picture. Webb cannot directly test quantum gravity. Its observations are of objects that are large and relatively cold by particle physics standards, galaxies, black holes, gas clouds. But the initial conditions of the universe, the fingerprints of whatever physics operated at the Planck scale in the first moments of existence, are imprinted in the structures we observe today. The distribution of galaxies, the pattern of the cosmic microwave background, the statistical properties of the large-scale structure of the universe, all of these are, in a sense, fossil records of the earliest moments of cosmic history. If quantum gravity leaves a signature in those initial conditions, if different theories of quantum gravity predict subtly different patterns of structure, then sufficiently precise observations of the large-scale universe could, in principle, discriminate between them. Not directly, not cleanly, not easily, but in principle. Webb is one piece of that puzzle, not the whole puzzle, that will require combining Webb's observations with those of many other instruments, including future experiments like the Euclid Space Telescope, the Vera-Rubin Observatory, and the Square Kilometre Array. But one piece, and every piece matters. Every data point is a constraint on whatever theory eventually emerges to reconcile gravity and quantum mechanics, and give us a truly complete picture of the universe from its first moments to its ultimate fate. That theory does not yet exist, but the observations that will eventually force it into existence, that will make it necessary, that will define the territory it must cover, are being made right now by Webb, by the other great instruments of this generation, by the accumulated effort of thousands of scientists working at the frontier of human knowledge. The theory is coming. We don't know its shape yet, but the data is already drawing its outline. There is a particular kind of silence that settles over you when you truly sit with the scale of what we have been discussing. Not the silence of emptiness, the silence of depth, the kind that comes when the mind has been stretched far enough that ordinary thoughts feel small by comparison, when the mental furniture of daily life, the appointments and obligations and small anxieties, temporarily loses its grip and something larger and quieter takes its place. If you're still with me at this point in the night, you've travelled a considerable distance. We have moved from the surface of things, the beautiful images, the golden mirrors, the Christmas morning launch, down through layer after layer of what those images actually mean, through the Hubble tension and the massive early galaxies and the oversized black holes and the chemical anomalies and the epoch of reionization and the cosmological principle and the incompatibility of general relativity and quantum mechanics, each layer deeper than the last, each layer more fundamental, each layer pointing toward the same quiet conclusion, that our map of the universe, extraordinary as it is not the territory. Let's slow down now. Let's sit with something that doesn't require equations or technical vocabulary, something that is simply true and simply worth holding for a moment. The universe is approximately 13.8 billion years old. In that time it has expanded from a state of unimaginable compression into a cosmos containing somewhere between 1 and 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially orbited by planets, some of those planets potentially harbouring conditions suitable for chemistry complex enough to call itself alive. And on one of those planets, a small, wet, geologically active world orbiting an unremarkable star in the outer arm of a spiral galaxy. A species of primate developed, over a few million years, the cognitive capacity to ask questions about its own origins, to look at the sky and wonder, to build instruments of increasing sophistication and point them at the darkness, and try to understand what was there before they existed and how it all began. That is what is happening right now. That is what Webb represents. Not just a telescope, a species asking a question, the universe, through the medium of human curiosity and human ingenuity, examining itself. There is something almost unbearably poignant about that, if you let yourself feel it. The fact that the universe produced inside itself beings capable of wondering about it. Beings who built a golden mirror and sent it 1.5 million kilometers into the void, specifically to look at light that has been traveling for 13 billion years, light that left its source before the Earth existed, before the Sun existed, before the Milky Way had taken its current shape, and ask what it means. And what Webb is finding, in the deeper sense, is that the universe is more than we thought, more complex, more surprising, more resistant to our frameworks, not in a way that defeats us, in a way that challenges us to think harder, look deeper, build better tools and better theories. This is what science is. Not a fixed body of knowledge, not a collection of settled answers, but a process. A conversation between the human mind and the universe it finds itself inside. A conversation that has been going on for thousands of years and shows no sign of ending. And right now, in this particular moment, that conversation has reached a point of extraordinary intensity. because Webb is asking questions that our best theories cannot yet answer. And that means the next answers, whenever they come from whatever direction, will change something fundamental about how we understand our place in the cosmos. We have spent a great deal of this journey looking outward, looking at the larger scales, galaxies, cosmic expansion, the structure of the observable universe, the first moments after the Big Bang. But there is another direction Webb is looking that deserves attention, a direction that is, in some ways, closer to home, a direction that touches on one of the oldest and most persistent questions our species has ever asked. Are we alone? Webb was not designed primarily as an instrument for the search for life. Its primary mission is cosmological, understanding the early universe, the formation of galaxies and stars, the large-scale structure of the cosmos. But it has capabilities that make it uniquely powerful for a related but distinct purpose: the characterization of planetary atmospheres around other stars. The technique is called transmission spectroscopy. When a planet passes in front of its host star, so transit, the starlight filters through the planet's atmosphere before reaching our telescopes. Different molecules in the atmosphere absorb different wavelengths of light, leaving characteristic fingerprints in the spectrum. By analysing the spectrum of starlight during a transit and comparing it to the spectrum outside of transit, astronomers can identify which molecules are present in the planet's atmosphere. This is not science fiction. It has been done. Webb has already detected carbon dioxide, water vapour, sulfur dioxide, and other molecules in the atmospheres of exoplanets, planets orbiting other stars. These detections have been confirmed and represent genuine landmark achievements in planetary science. But the Holy Grail, the detection that would electrify the scientific community and perhaps shake human civilization at its foundations, would be the identification of what are called biosignatures, chemical signatures in a planetary atmosphere that are difficult or impossible to explain without invoking biological processes. Oxygen is the classic example. In the presence of ultraviolet radiation and geological processes, oxygen tends to be consumed, locked up in rocks and other molecules. To maintain a significant concentration of free oxygen in an atmosphere over geological timescales typically requires a continuous source. On Earth, that source is photosynthesis, billions of years of biological activity converting carbon dioxide into oxygen and organic matter. If Webb detected a significant concentration of oxygen in the atmosphere of an Earth-sized planet in the habitable zone of its star, the range of distances where liquid water could potentially exist on the surface, it would be among the most significant observations in human history. Webb has not made that detection, not yet. The planets it has characterized atmospherically are mostly hot Jupiters, large gas-rich planets orbiting very close to their stars, where conditions are wildly incompatible with life as we understand it. The small, rocky, potentially habitable planets are much harder to study. Their atmospheres produce much weaker spectroscopic signals, and multiple transits need to be observed and combined to build up a detectable signal. But Webb is accumulating those observations, quietly, patiently, transit by transit, spectrum by spectrum, and it has years of operational life ahead of it. Years in which the cumulative data on rocky planets in habitable zones will grow, and the sensitivity of our atmospheric characterizations will improve. We may be closer to an answer to that oldest of questions than any previous generation has ever been. Not certain of finding life, the universe may yet turn out to be biologically sparse in ways we cannot currently evaluate, but closer, with better tools, better techniques, better data than our predecessors could have imagined. And whatever Webb finds, whether it detects the unmistakable signature of biology on a distant world, or whether it finds atmosphere after atmosphere devoid of biosignatures, quietly suggesting that life may be rarer than we hope, that finding will be one of the defining data points of human intellectual history. The answer is out there, encoded in the light of distant stars, waiting to be read by a golden mirror floating in the cold darkness between worlds. Let's talk about something that rarely makes it into popular accounts of Webb's discoveries, but that sits underneath all of them like a quiet foundation. Let's talk about what it actually means to see the early universe. When Webb observes a galaxy at a redshift of 8 or 10 or 12, numbers that correspond to epochs when the universe was only a few 100 million years old, it is not simply taking a photograph of a distant object the way a camera takes a photograph of a mountain. The situation is far stranger than that, and understanding the strangeness is worth the effort. Light travels at a finite speed, approximately 300,000 kilometers per second in a vacuum. This is not a limitation of our technology or our understanding. It is a fundamental feature of the universe, built into the fabric of space-time by the same equations that describe everything else. Nothing carrying information can travel faster than light, and this means that every observation we make is necessarily an observation of the past, not metaphorically, literally. When Webb detects the light from a galaxy at a redshift of 10, it is detecting photons that left that galaxy approximately 13.2 billion years ago. The universe was roughly 500 million years old when those photons began their journey. They have been travelling through expanding space ever since, and as space expanded, their wavelengths stretched with it, shifting from the ultraviolet into the infrared, which is precisely why Webb, an infrared telescope, is so perfectly suited to detect them. But here is where it gets stranger. The distance to that galaxy is not simply 13.2 billion light years, even though the light took 13.2 billion years to reach us. Because space has been expanding during those 13.2 billion years, the galaxy that emitted that light is now much farther away than it was when the light left it. Current estimates put the co-moving distance, the distance as measured in today's expanded universe, to objects at the highest redshifts Webb observes at over 30 billion light years. Think about what that means. We're seeing an object as it was 13.2 billion years ago, and that object is now more than 30 billion light years away, meaning it is moving away from us faster than the speed of light. Not because anything is travelling through space faster than light. That remains impossible, but because space itself is expanding, and at sufficiently large distances, the cumulative expansion of all the space between us and a distant object can carry that object away from us faster than light can cross the intervening distance. This is not a loophole or a paradox. It is a straightforward consequence of general relativity applied to an expanding universe. But it means that the objects Webb is observing at the highest redshifts are, in a very real sense, forever beyond our reach. We will never be able to travel to them. We will never receive any signal they emit after a certain point in time. They are visible to us only through this ancient light, this fossilized photon record of a universe that no longer exists in that form. What Webb is doing, then, is archaeology, cosmic archaeology. It is sifting through the fossil record of light, ancient photons preserved across billions of years of cosmic expansion, and reconstructing from them the history of a universe that is, in its earliest chapters, as inaccessible to us as the moment before the first word of a story we arrived late to hear. And yet we are reading it, imperfectly, incompletely, but genuinely reading it, extracting real information from ancient light about real structures that really existed in a universe that was young and hot and turbulent and full of the violent energy of formation. There is something almost unbearably beautiful about the fact that this is possible at all. that the laws of physics allow information to be preserved across such distances and such timescales, that a photon can travel for 13 billion years through an expanding universe, arrive at a golden mirror floating in the cold shadow of a planet orbiting an unremarkable star, and deliver a message about the universe's infancy. The universe has been sending us these messages for as long as light has been travelling. We are only now, with Webb, becoming capable of reading them with sufficient clarity to begin understanding what they say. By now the night has probably deepened around you. The sounds of the world outside have likely faded further. The quality of the darkness in your room, if you have been listening in the dark, has probably settled into something more complete. That particular late-night darkness that feels different from the darkness of the early evening, heavier and more private, as if the world has finally stopped performing and simply rested. This is a good moment to let things slow down a little, to let the ideas we have been moving through settle, the way sediment settles when water stops moving, gently, without effort finding its level. We have covered a tremendous amount of ground. We started with the silence of a night sky and the strangeness of looking at light that has travelled billions of years. We moved through the history of the Big Bang model, how Hubble discovered the expanding universe, how scientists built a detailed picture of cosmic evolution over nearly a century of observation and theory. And then we followed Webb into the early universe and watched, discovery by discovery, as that picture began to develop unexpected tensions, unexpected structures, unexpected challenges to things we thought we knew. The Hubble tension, the massive early galaxies, the oversized early black holes, the chemical abundances that evolved faster than our models allow, the Ryanization epoch and its surprising efficiency, the questions about dark matter, modified gravity, the cosmological principle, quantum gravity, the search for biosignatures on distant worlds, the cosmic archaeology of ancient light. It is a lot to hold, and you don't need to hold all of it with equal weight right now. Some of it will have landed more strongly than other parts. Some of it will resurface later, tomorrow, or next week, or in a moment when you look at the night sky, and something you heard tonight comes back to you with a new clarity. That is how this kind of learning works, not through immediate total comprehension, but through a slow absorption, through the ideas working their way into the background of how you see things, quietly rearranging the furniture of your understanding until one day you look at something familiar and see it different. What Webb is doing to cosmology is something like that. Not a sudden revolution, not yet, perhaps not ever in a single dramatic moment, but a slow, persistent rearrangement, a gradual accumulation of observations that don't quite fit, that push and pull at the existing framework, that demand explanation and resist easy ones. Science is patient in this way. It doesn't always deliver its revelations on demand. Sometimes it works for decades on a problem before the solution appears. Sometimes the solution comes from an unexpected direction, from a piece of mathematics developed for a completely different purpose, from an observation made while looking for something else entirely, from a young researcher who looks at familiar data with fresh eyes and asks a question no one thought to ask before. The solution to what Webb is finding, the explanation for the Hubble tension, for the massive early galaxies, for all of it, will come from somewhere, from someone, perhaps from someone who's alive right now, sitting in a graduate school office or staring at a laptop in a coffee shop, or lying awake at night thinking about numbers that don't add up. Perhaps from someone who listened to something like this, once, and felt the pull of the question strongly enough to spend a life trying to answer it. There is a concept in physics called a singularity. In the mathematical sense, a singularity is a point where a function or equation breaks down, where the values it produces become infinite or undefined, where the normal rules stop applying and the mathematics signals clearly and unambiguously that it has reached the edge of its own validity. General relativity contains singularities. At the centre of a black hole, according to the equations of general relativity, the density of matter becomes infinite, the curvature of space-time becomes infinite, and the theory simply stops being able to say anything meaningful about what is there. Similarly, if you run the equations of cosmic expansion backward in time, if you rewind the universe toward its beginning, you reach a point where the density and temperature become infinite, where time itself may cease to have its ordinary meaning. These are not physical infinities. No one seriously believes that anything in nature is actually infinite. They are mathematical infinities, signals that the theory is being applied outside the domain where it is valid. They are the equation's way of saying, something else is happening here that I don't have the tools to describe. Physicists call these singularities problems, but they are really opportunities. They are the precise locations where a deeper theory is needed, where the existing framework, however successful, has reached its natural limit and must be replaced or extended by something more fundamental. The singularity at the beginning of the universe is, in this sense, the deepest question in all of physics. What happened at the Big Bang? What happened before it? If before even has meaning when time itself may have begun at that moment? What determined the initial conditions of the universe, the specific values of its physical constants, the precise pattern of its initial density fluctuations, the particular balance of matter and antimatter and energy that allowed the cosmos to evolve in the way it did, rather than in any of the countless other ways it might have? These questions sit at the intersection of cosmology, quantum mechanics, and philosophy, and they do not yet have answers. They have proposals, speculative, creative, mathematically sophisticated proposals, but no confirmed answers. One of the most remarkable proposals is the idea that our universe is not the only one. The concept of a multiverse, a vast ensemble of universes, each with its own physical laws, its own constants, its own history, arises naturally from several independent lines of theoretical reasoning. In inflationary cosmology, the process of rapid expansion that set up the initial conditions of our universe may be eternal, continuously generating new regions of space that each undergo their own Big Bang and evolve into separate universes, disconnected from ours and from each other, expanding away faster than light can bridge the gap between them. This is called eternal inflation, and it implies a multiverse of staggering size and variety. In string theory, the landscape of possible vacuum states, the different ways the extra dimensions of the theory can be compactified and stabilized, is estimated to contain something like 10 to the power of 500 distinct configurations. Each configuration corresponds to a universe with different physical constants, different particle masses, different force strengths, a number so large it cannot be meaningfully written out, each element representing a different universe with different rules. In quantum mechanics, the many worlds interpretation proposed by Hugh Everett in 1957 and still debated today suggests that every quantum event that can go multiple ways actually does go multiple ways, with the universe splitting into branches at each such event, each branch evolving independently and containing observers who experienced a different outcome. These are very different proposals. They arise from different theoretical contexts, make different predictions, and have different relationships to empirical testability. What they share is the implication that our universe, the one we observe, the one Webb is exploring, may be just one instance of something far larger, one bubble in an ocean of bubbles, one chapter in a story that has no single beginning and may have no end. Webb cannot directly test the multiverse hypothesis. No current or foreseeable instrument can. The other universes, by definition, are beyond our observational horizon, causally disconnected from ours. But the multiverse idea influences how we think about the questions Webb is raising. If the physical constants of our universe are not uniquely determined by some deeper principle, but are instead random draws from a vast landscape of possibilities, then asking why they have the values they do may be the wrong question. The answer might simply be, because in universes where they had different values, observers like us didn't arise to ask. This is called the anthropic principle, and it is one of the most controversial ideas in modern physics. Some find it profound, others find it empty, a way of explaining everything by predicting nothing. The debate is genuine and unresolved, but Webb is providing data that will eventually bear on these questions. By measuring the physical constants and the cosmological parameters of our universe with ever-increasing precision, by mapping the large-scale structure of the cosmos and comparing it to theoretical predictions, by identifying anomalies that point toward missing physics, Webb is narrowing down the space of viable theories, and whatever theory eventually emerges will have something to say about whether our universe is unique or one of many, whether its properties are inevitable or contingent, whether the questions we're asking have answers or only more questions beneath them. The night is deep now. If you have been with this journey from the beginning, you have been listening for a long time, and there is something that happens in the late hours when the mind has been engaged with large ideas for an extended stretch, a kind of softening. The sharp edges of analytical thinking gradually become less insistent. The ideas that arrived with full clarity and precision begin to settle into something more impressionistic, more felt than thought, less like information being processed, and more like atmosphere being absorbed. This is not a loss of understanding. It is a different kind of understanding, the kind that happens not in the foreground of attention, but in the background, the kind that doesn't announce itself but simply becomes part of how you see things. Let the ideas settle in that way now. We've been talking about the universe, its age, its structure, its anomalies, its mysteries. But there is something we haven't said explicitly that runs underneath everything, like a current beneath the surface of a river. Something that all of these discoveries, all of these tensions and anomalies and unanswered questions point toward in a quiet but unmistakable way. The universe is under no obligation to be simple. We often approach nature unconsciously without quite realizing it, with an assumption of simplicity. We expect at some level that the deepest laws will be elegant, that the fundamental equations will be beautiful, that reality, properly understood, will resolve into something clean and unified and comprehensible. This expectation is not unreasonable. It has served science well. The history of physics is full of moments where simplicity emerged from apparent complexity, where disparate phenomena were unified under a single elegant principle. But nature has also consistently turned out to be stranger than expected. Quantum mechanics is not simple. It is deeply counterintuitive, requiring us to abandon our everyday intuitions about what it means for something to have a definite position or a definite velocity. General relativity is not simple. It requires us to think of gravity not as a force, but as the curvature of a four-dimensional space-time continuum. The standard model of particle physics Our best description of the fundamental constituents of matter and the forces between them is not simple. It is a complicated, somewhat inelegant structure with many free parameters that must be measured rather than derived. And yet these theories work. They describe reality with extraordinary precision. Their lack of simplicity is not a flaw. It is the shape of what is true. Webb is adding to this picture. It is showing us that the early universe was not simple, that galaxy formation, black hole growth, chemical evolution, reionization, these processes were not the clean, orderly, well-behaved phenomena our models assumed. They were messy, efficient, surprising, full of variations and extremes that challenge our frameworks. The universe in its youth was wilder than we imagined, more energetic, more productive, more capable of building large structures quickly than our models suggested was possible. It was not the quiet, orderly nursery of gradual structure formation that the standard picture implied. It was something more turbulent, more dynamic, more alive with activity. And perhaps that wildness, that excess of structure, that efficiency of formation, that apparent violation of the timelines we drew up for it, is telling us something not just about galaxy formation, but about the nature of the initial conditions themselves. About what the universe was like in its very first moments. About what happened at or before the singularity that our equations cannot reach. The early universe was trying to tell us something. It has been trying to tell us for 13.8 billion years, encoded in the light it has been sending in all directions since its first stars turned on. We are only now, with Webb, beginning to read that message with enough clarity to sense what it might be saying. And what it seems to be saying, quietly, persistently, in the language of anomalies and tensions and numbers that don't quite add up, is this: you don't know me as well as you think you do. Look again. Look deeper. Ask better questions. There is a researcher named Alexei Filipenko who once said something that has stayed with me. He said that we are living in a golden age of astronomy, not because everything is going well, not because the answers are coming easily, or the models are holding up neatly under the pressure of new data, but precisely because they are not. Because the questions are getting harder, and the instruments are getting better, and the gap between what we observe and what we can explain is widening in exactly the way it does when a field is on the edge of something genuinely new. Golden ages in science don't look like periods of smooth, comfortable progress. They look like this. They look like Webb. They look like a telescope that was designed to confirm and refine our existing picture of the universe, and instead began, quietly and systematically, to complicate it, to add texture where we expected smoothness, to reveal structure where we expected emptiness, to find mass where we expected youth and darkness, and to measure expansion rates that refuse to agree with each other, no matter how carefully we check the arithmetic. There is a long history of moments like this in science, and looking back at them now, from the comfortable vantage point of knowing how they resolved, they all share a common feature. In each case, the anomaly that seemed most troubling, the number that most stubbornly refused to fit, turned out to be the most important clue, the thing that pointed most directly toward the new understanding that was waiting to be born, the anomalous precession of Mercury's orbit, the tiny unexplained deviation from what Newtonian gravity predicted, pointed toward general relativity. The anomalous results of the Michelson-Morley experiment, the failure to detect the motion of Earth through the luminiferous ether, pointed toward special relativity. The anomalous stability of the atom, the fact that, according to classical electromagnetism, electrons orbiting a nucleus should radiate energy and spiral inward in a fraction of a second, pointed toward quantum mechanics. In each case, a small, persistent, uncomfortable anomaly was the fingerprint of a deeper truth. A truth that, once revealed, did not just explain the anomaly, but transformed the entire landscape of physics, opening up territories of understanding that the previous framework couldn't even see. The Hubble tension is an anomaly. The massive early galaxies are anomalies. The oversized early black holes are anomalies. The chemical evolution that proceeded too fast, the reionization that was more efficient than expected, the initial conditions that seem to have been more concentrated than the standard inflationary model predicts, all anomalies, all persistent, all carefully checked, all refusing to go away. History suggests that somewhere in this collection of anomalies there is a fingerprint, a clue, a thread that, when pulled with sufficient care and insight, will begin to reveal the shape of whatever is missing from our current picture. We don't know which anomaly contains the key. We don't know whether the solution will be a small modification to an existing theory or a wholesale replacement of several foundational ideas. We don't know whether it will come in 5 years or 50, from a theorist working alone, or from a large international collaboration processing petabytes of observational data. But we know it will come, because it always has, because the history of science is, at its deepest level, a history of anomalies becoming revelations, of numbers that didn't add up becoming the first equations of a new understanding. And Webb is giving us the anomalies, precisely measured, carefully documented, stubbornly real. It is doing its part. Now it is up to the human minds on the other end of its data stream to do theirs. The golden mirrors are still turning, not literally. The James Webb Space Telescope doesn't rotate in any dramatic sense. It holds its position with extraordinary precision, making tiny adjustments with small thrusters and reaction wheels to keep its instruments pointed at whatever target the current observation program requires. But metaphorically, the mirrors are always turning, always gathering light, always adding to the archive of ancient photons that humanity is slowly learning to read. As of now, Webb has been operational for a little over 3 years. Its original design lifetime was 10 years, with a goal of 5. But the launch was so precise, the rocket delivered it to its destination with such accuracy, that it used far less fuel than anticipated for the trajectory corrections that were needed along the way. Current estimates suggest that Webb has enough fuel to operate for 20 years or more. 2 decades of observations, 2 decades of looking at the early universe, at forming galaxies, at exoplanet atmospheres, at all the phenomena that fill the space between the first light and the present moment. 20 years is a long time in science. It is long enough for an entire generation of researchers to come of age with Webb's data as their primary observational resource. Long enough for theoretical frameworks to be built, tested against the data, revised, and rebuilt. Long enough for the anomalies we've been discussing to either deepen into undeniable crises or resolve into satisfying explanations. Long enough, perhaps, for something genuinely new to emerge. In that time, Webb will not be alone. The next decade will see the commissioning of several major new observatories that will work alongside it and extend its reach. The extremely large telescope currently under construction in the Chilean Atacama Desert will be the largest optical and infrared telescope ever built. With a primary mirror 39 meters across, it will collect more light in a single second than Webb collects in several minutes, and its adaptive optic systems will allow it to achieve image sharpness that surpasses even Webb in certain wavelength ranges. It will be able to characterize exoplanet atmospheres in ways that complement Webb's space-based observations. The Vera Rubin Observatory, also in Chile, will conduct a 10-year survey of the entire southern sky, cataloguing billions of galaxies and providing an unprecedented map of the large-scale structure of the universe. The kind of map that will either confirm or challenge the cosmological principle, that will sharpen the constraints on dark energy models, and that will provide the statistical foundation for understanding whether the anomalies Webb has found are representative of the universe at large or limited to specific regions or epochs. The Square Kilometre Array, a radio telescope network being built across South Africa and Australia, will observe the universe in radio wavelengths with a sensitivity and resolution that will open entirely new windows onto the early universe, the epoch of reionization, the distribution of neutral hydrogen across cosmic time. And there are proposed space missions, some approved, some still being designed, that would extend humanity's observational reach further still. Missions to directly image Earth-like planets around nearby stars. Missions to measure the cosmic microwave background with even greater precision. Missions to detect the gravitational wave background from the earliest moments of the universe. A background so ancient that it would be, if detected, a direct record of the physics of inflation itself. We are building, instrument by instrument, observation by observation, a picture of the universe that no single generation could have assembled alone. Each generation adds its layer, its technology, its insights, its carefully measured numbers, to a structure that grows taller and more detailed with each passing decade. And at this particular moment, at this particular point in that multi-generational project, Webb is the brightest light we have, the sharpest eye, the deepest reach, floating in the cold darkness beyond the moon, gathering ancient photons with its golden mirrors, sending the data home at the speed of light to the scientists and students and curious minds who are trying to understand what it all means. The universe is speaking. In the language of light and redshift and spectral lines and galaxy morphologies and chemical abundances and expansion rates that don't agree. It has been speaking for 13.8 billion years. We are finally, with instruments like Webb, becoming capable of listening carefully enough to begin to hear what it is saying. And what it is saying, beneath the anomalies and the tensions and the numbers that don't add up, is something that every great mystery has always said to every curious mind that has ever stood at its edge and looked in. There is more. Keep looking. We've travelled a long way tonight. We started in the silence of a night sky, that particular silence that settles over you when you look up and realise that what you're seeing is not the present but the past. Light that left its source millions or billions of years ago, crossing an unimaginable distance to reach your eyes in this moment, on this night, in whatever quiet corner of the world you've been listening from. And from that starting point we went deep, through the history of how we came to understand the expanding universe, through the extraordinary engineering achievement of a golden telescope floating 1.5 million kilometres from home, through the discoveries that have unsettled cosmology in ways that are still being reckoned with, the galaxies that are too massive too soon, the expansion rate that disagrees with itself, the black holes that grew too fast, the chemical elements that appeared before they should have, the ancient light that carries messages we're only now learning to decode. We sat with the strangeness of looking at a universe that is 95% invisible to us. We considered the possibility that our maps of the cosmos, as extraordinary as they are, as hard-won and carefully constructed, may need to be redrawn in ways we cannot yet fully anticipate. We thought about what it means to live at this particular moment in history, when the instruments we have built are finally sensitive enough to hear the universe saying things that contradict what we thought we knew. And we ended, as all good journeys into the unknown should end, not with an answer, but with an invitation. There is more. Keep looking. That invitation is not just for the scientists. It is not just for the researchers who will spend their careers working through Webb's data, building theories, running simulations, arguing at conferences, and writing papers that will slowly, incrementally, move our understanding forward. It is for everyone who has ever looked at the night sky and felt something: curiosity, wonder, vertigo, the particular kind of longing that comes from sensing that the universe is vast beyond comprehension, and that you are somehow part of it. You are part of it. That is perhaps the most important thing to carry away from everything we have discussed tonight. The universe did not just produce the stars and the galaxies and the black holes and the expanding space. It produced inside itself beings capable of wondering about all of it. Beings who built telescopes. Beings who asked questions that took centuries to answer and then asked harder ones. Beings who launched a golden mirror into the void on Christmas morning and waited, breathlessly, for it to show them something they had never seen before. That is you. That is your species. That is what it means to be a human being alive in this particular era of cosmic history. To be among the first generation of creatures in the universe, as far as we know, capable of reading the ancient light and beginning to understand the story it tells. The story is not finished. It will not be finished in our lifetimes, or perhaps in any lifetime. The universe is too large, too old, too strange, too full of things we have not yet imagined asking about. But every piece of it that we understand is a genuine victory. Every anomaly that becomes an explanation is a step forward. Every question that turns out to be deeper than expected is a reminder of why we keep asking. Webb will keep looking. The data will keep coming. The scientist will keep working. And somewhere in that accumulated effort, in some paper, in some observation, in some late-night moment when a researcher stares at a number that doesn't fit and suddenly sees for the first time why, the next piece of this extraordinary puzzle will fall into place. And when it does, it will change how we see everything. Tonight, wherever you are, whether you're already drifting towards sleep, or hovering in that gentle borderland between wakefulness and dreaming, or still quietly alert in the darkness, take a moment before you go, not to think about anything in particular, just to be aware of the sky above you, even if you cannot see it from where you are, aware that it is there, infinite and ancient and full of light that has been travelling toward this moment for longer than the Earth has existed. You are on a small planet orbiting an ordinary star in the outer arm of one of 2 trillion galaxies, and you spent part of this night thinking about the universe that contains you. That is not a small thing. That is one of the most remarkable things a creature in this universe can do. If this journey meant something to you, if something we discussed tonight sparked a question, or settled something that had been vague, or simply gave you a few hours of the particular pleasure that comes from thinking about large things in the quiet of the night, then let me know in the comments where you listened from. What city, what country, what corner of this small and extraordinary planet? I love knowing where these words travel to. And if you are not yet subscribed, now is a good moment. There are more journeys ahead, more questions worth sitting with, more corners of science and nature and human understanding worth exploring together in the quiet hours. The subscribe button is there, and it costs nothing, and it means the next journey will find you when it arrives. Leave a like if this felt worth your time. It is a small thing that makes a real difference in whether these videos find the people who would want to hear them, and wherever you are, whatever time it is, however close or far from sleep. Thank you for being here. Thank you for being curious. Thank you for spending part of your night thinking about the universe. It noticed. Good night.